race to win wars and explore the stars, have created some of the most fantastic products ever designed, and we use them every day, unaware of their amazing origins. On Wicked Inventions. Radio. Why World War I helped kickstart our love of listening to the radio. Silly Putty. How a wartime search for synthetic rubber led to the discovery of a children's favourite. The Jerry Can. A World War II German design classic that was so good even their enemies started using it. We reveal the amazing science and manufacture behind these wicked inventions. Radio. It's everywhere, literally. A wireless transmission of energy travelling through space, aiding communications worldwide and beyond. In the modern world, we're surrounded by radio waves of all kinds. From communication to navigation, radio has become a vital part of how we live our lives today. But how were these waves discovered? And what role did warfare play in their development? In 1864, Scottish scientist James Clerk Maxwell demonstrated via mathematical theory that electromagnetic waves could travel through space. Nearly 2 decades later, Heinrich Rudolf Hertz was able to confirm the existence of these waves in an experiment. Much experimentation with these Hertzian or radio waves ensued, and in 1894, Italian inventor Guglielmo Marconi began working on a wireless telegraphy system based on these waves. By 1896, he had gained a patent for his system, and it was then developed commercially over the next few years.
Radio really is creating kind of waves in that electromagnetic spectrum and using those waves you create in the spectrum to encode messages and send information, messages or voice or whatever it is across the electromagnetic spectrum between a sender and a receiver. And that is ultimately what radio is.
The basic principle behind radio transmission is converting information, such as sound, into an electromagnetic signal via a transducer, which is then transmitted as an electromagnetic radio wave. A receiver then intercepts this wave and extracts the electronic signal that is then converted back into sound by another transducer, such as a speaker. The earliest practical use of radio transmission was used on the seas, as telegraphic messages were sent between ships and to receivers on land via Morse code. Probably the most famous nautical use of radio transmissions was in 1912 with the infamous sinking of the Titanic. The ship was fitted with state-of-the-art radio equipment that proved vital in sending out distress signals and relaying news on survivor numbers to the nearest ships and shores. 2 years later, in 1914, radio was to play a huge part in the trenches of World War I, with transmissions between troops initially being sent through cumbersome, ground-laid cables that could be easily destroyed or, worse still, intercepted. A better alternative was needed. The development of radio communications was accelerated greatly during the war. Due to some of the modern innovations in World War I, radio proved vital in communicating with moving tanks and troops in a way that cable systems simply couldn't ever hope to achieve. By the end of the war in 1918, the wireless sets had come on a great deal since 1914. By the 1920s, radio was beginning to be used widely as a home appliance and became an important mass medium for entertainment and news. Its development would again be accelerated during World War II. As well as being used for land and sea communications, its use was extended further to aircraft communications, navigation, radio, and even television. Since this time, developments in the use of radio transmissions have continually been made, and in the early 21st century, we find ourselves making a change from analog to digital radio transmissions.
Analog technology, or analog radio in particular, the signal that you create, in this case our radio signal, is a direct reflection of what happens in the world, with the actual signal around us. And so we take that signal and we send it as is to the receiver, who then translates it, in this case via a loudspeaker, into an audible signal again. With digital we use a very different way of representing information, where information is represented in the case of binary digital technology, which is what we use predominantly in today's world, where the information is represented as a set of discrete values, in this case ones and zeros. This is less prone to interference and error. It is easier with digital signals to send reliable information from one point to another point.
One manufacturer of digital radios is Pure. producing radios from their headquarters in China to ship to customers worldwide.
In 2002, Pure didn't exist. It literally didn't exist as a company, and then we just went straight out and tried to manufacture the first radios, the first wooden box radios, and then we actually just created the digital radio market from there. And from now, there are many, many manufacturers of digital radio, from own brands to well-established brands.
Once the case and cabinet of the digital radio has been manufactured, as well as all the plastic components, the production of the full unit can commence, beginning with the building of the PCB, also known as a printed circuit board. Solder paste is wiped across an etched screen that allows the paste to be applied to the relevant locations of the bare PCB. The boards are then moved into a pick-and-place machine, where components are picked from reels and placed into the appropriate position. Once the pick-and-place machine has done its work, the boards are moved to a reflow oven that melts the solder paste and fixes the components to the board.
Each of the connections uses a copper trace to connect between them, a copper track that's the width of a human hair, which is about 0.1 of a millimetre. So when this is complete and it's been fully soldered and manufactured, they've got to be tested. So it then moves on to an automatic optical testing machine, and that will robotically test with a visual system every single component on that product. So it will check, one, that it's present, and two, that it's soldered down correctly. It then moves to another checking system that will simulate being inside a radio. You don't want to build it into the radio if it doesn't actually work. Even though all the components have been placed correctly, there might be a problem with the component. So this test station, it injects RF signals, it injects audio signals into the printed circuit board, and we look at the output and see whether it's within set limits. If it's within those limits, we know that it will be good when it goes into the final radio.
The rest of the process in the production of a pure digital radio is all by hand, ensuring meticulous quality control. The workers assemble all of the pre-made components together on a production line in order to construct the final unit. All of the electronic components of the radio are interconnected via cables, such as the PCBs, the OLED display, and the loudspeaker. These are then fixed into place, and the mechanical parts are screwed in. Once the radio has been assembled, the completed unit is turned on and tested for functionality. This includes testing that a signal is being picked up by the signal generator in the factory, the audio is working, and the display is functioning in the correct manner. Once the radio has passed these tests, it is boxed up into retail cartons, along with guides and protective packaging. The pure radio is then ready to be enjoyed by consumers, primed to pick up radio signals from across the globe. Sometimes a product is developed from the needs of war, or another may have entered our lives after helping scientists explore the stars. Well, the next item ticks both these boxes. It is a gooey, bouncy, solid substance, a byproduct of World War II, used by astronauts, and yet best known as a children's toy. It is Silly Putty. It all started in World War II, a conflict that placed greater emphasis on military mobility. And with that came greater demands on materials. Men needed boots, vehicles needed wheels, and planes and ships needed air and watertight seals. And the best materials to use? Natural rubber, and lots of it.
We're talking tons and tons of rubber that were used in a battleship. Half a ton was used in an airplane, 35 pounds was, say, used for the footwear and all the gear for a soldier. If you're supplying an army that's 100,000 strong, you suddenly need a lot of rubber and you need it fast because it's used in a harsh environment where it may wear out quite quickly.
The problem for America as they entered the war in 1941 was that their enemy, Japan, controlled most of the world's natural rubber plantations in the wake of their successful invasion of Southeast Asia. The only way for the United States to satisfy their rubber demands was to manufacture man-made or synthetic rubber on an industrial scale. With the cooperation of some of the biggest chemical companies in America, the race was on to find a suitable rubber alternative, and the material we now know today as Silly Putty was the result of experiments into finding the perfect rubber substitute.
Silly Putty was made as an accidental discovery in the pursuit of rubber. It was a compound that didn't work and have the properties they wanted. Basically, it was a material that goos all over the place, is quite sticky, and so doesn't really have the properties you want to use for rubber for replacement in the war. And so it was left. There was no use for it, there was no war use for it, and they left it to the side.
The material's initially useless properties may explain why the credit for its invention is confused, with Dow Corning chemist Earl Warwick and General Electric's inventor James Wright both claiming the honour. But what they had both independently discovered was that when boric acid reacted with silicon oil, the gooey, bouncy substance we call silly putty was created.
Silly putty is a mixture, it's a reaction actually in a polymer of boric acid and siloxane oils. Now what that does is that produces silicon oxygen bonds which are very, very flexible. They can bend in and out, which is why silly putty is very, very stretchable. And it also has a little bit of water in it, so it sort of melts and flows quite nicely past each other.
Silly putty's unique properties stem from its viscosity, or thickness as we may informally call it. This describes how a material resists flow at certain temperatures. Think of honey becoming runnier when warmed. This is classed as something called a Newtonian fluid. In silly putty's case, viscosity is additionally influenced by force being applied and is subsequently classed as a non-Newtonian fluid. In other words, over long flow times or at high temperatures, silly putty behaves like a highly thick fluid. But over short flow times or at low temperatures, it behaves like an elastic solid and gives the putty its quirky characteristics. The putty was to remain a curiosity among the scientific world until 1949, when toy store owner Ruth Forgatter came across the fun material and enlisted the help of marketing consultant Peter Hodgson to unleash the product's commercial potential.
So Peter Hodgson, the marketing consultant for the product, took out a loan of $147 to buy some additional product to try and package it up and sell it, and he renamed it then Silly Putty. It wasn't known as that beforehand. A bit later in the year, in 1950, there was a magazine article, and during that magazine article it talked about it, said what it was wonderful for, and the next 3 days he sold 250,000 of them at $1 a piece.
If you put it so, it'll go forever, like taffy. But if you give it a sharp tug, it'll break like a biscuit. And remember, nothing else is silly putty.
Even a brush with financial ruin caused by a silicon embargo during the Korean War in the 1950s couldn't stop the toy's success, and an estimated 300 million eggs, or 4,000 tons, have been sold since then. And the space connection? In 1968, the Apollo 8 missions became the first manned spacecraft to leave the Earth's orbit, reach the Moon's orbit, and return safely, and Silly Putty was put to valuable use on board.
Silly Putty was used in space to stick things in place. It's a nice flexible material. Under the influence of gravity in our house, it'll fall and just kind of become a goo. But in space, because there's not much gravity, or very, very little in a spacecraft, it'll just stick wherever you put it and hold whatever you want in place. And so NASA used it for putting tools in their place. You could stick it to a wall, you could stick it where it's handy. It was quite a convenient use of a modern, at that time, toy. And that's what a lot of NASA does. They take a product that's already used and repurpose it, and then sometimes it finds a way back into civilian life. But this time this was civilian life finding its way into NASA very usefully.
So, a material created during World War II, used in space and played with throughout the world. Silly Putty. Truly a wicked invention. We've just seen the story of Silly Putty and what makes it such a tremendous toy. But how easy is it to make a slimy putty yourself? And can we give it some magical magnetic properties? To begin, the ingredients. You will need white PVA glue, talcum powder, laundry gel, some work better than others, plastic spoons, wax paper, latex gloves, face mask, black iron oxide powder, magnet, plastic container, and wooden skewers. It can get messy, and for safety it is best to wear a pair of latex gloves. To begin, our intrepid tester needs to carefully mix his ingredients. The magical formula is 2 parts glue to 1 part laundry gel. He places 2 tablespoons of glue into a plastic bowl and adds 1 tablespoon of laundry gel and starts to mix the ingredients together. The mixture starts to solidify, but is still very wet, so we add some talcum powder to act as a binder. Our tester takes this mixture and kneads it with his hands to finish combining it, and then places it on the wax paper to dry out a little. At this point, we have created a silly slime, but let's give it some black magic, literally. The black iron oxide powder is very fine and not great to inhale, so after taking the necessary safety steps of donning a face mask and carefully decanting the powder, our tester places the slime back into the container and adds 2 teaspoons of the iron oxide. He then works it with his hands to create a new black slimy putty. Now the fun part, let's get the magnet. Because the iron oxide powder is ferrous, or magnetic to you and me, if we place a magnet close to the slime, it starts to move forwards towards it. Freaky stuff. If you try this at home, just remember that the slime can leave residue on surfaces and don't put it in your hair. Something that our intrepid tester doesn't have to worry about. Some of our best inventions have been born from the necessity of war. This particular invention has changed very little and has gone on to become an iconic tool of the garage and car. It is, of course, the jerry can.
During the war, Brits had a nickname for the German soldiers. It was jerrys. So Brits called the can used and designed by Germans a jerry can, which basically means Germans can.
During World War II, maintaining a supply chain was very important, particularly fuel to keep tanks and armoured vehicles on the move. The British fuel can of the time was made out of tin, and due to its complete unreliability, it was nicknamed the Flimsy because of its regular splitting and leaking. However, in the late 1930s, the Germans invested heavily into designing their own can, knowing its efficiency and value on the battlefield.
The jerry can was such a successful design. Far better than ours. Theirs held 20 litres of fuel. And if you put 20 litres of fuel into a can, there's a lot of pressure there. And the British petrol tins were renowned for splitting at the seam. Now the jerry can was 2 press sides that was joined together with an overlapping welded seam, and then it had a sealed cap to it. It could be stacked on its side or upright in racks. So they were very good at storing. They didn't burst. And you could use them for all the different kinds of fuel. Even you could have clean ones that could carry water for you.
The importance of this design was highlighted during the African campaign of 1940. German forces were at times heavily outmanned and outgunned. Their supplies coming to Africa were also being intercepted more often than not. Yet what fuel supplies they did have appeared safe in the jerry can and could be transported, reused and stored with ease. The Germans' efficiency with what little supplies they had led to the Allied forces making daring missions on German-held fuel depots to either destroy or often steal the infamous jerry can. It wasn't long before entire British divisions were equipped with jerry cans, ditching their own flimsies, which were reported to have cost the Allies 25% of their fuel in leakages alone.
Both the British and the Americans, the Allied forces, copied the Germans. Whenever we captured a German fuel dump, we didn't blow it up, we pinched all their tins. And then, of course, we manufactured them ourselves. You can still buy them to this very day. In fact, I've got one in my garden shed. Jerry cans, it's a fantastic design. They've simply kept it.
The jerry can is still hugely popular today. It has become an essential tool for the general public and the military. The Latvian manufacturer Valpro have been making these cans for many NATO armies around the world. It has been produced at the Valpro steel plant in Latvia since 1959, and they have made an estimated 30 million cans in that time.
Valpro is a metalworking company that is specialized in production of jerry cans that are made out of steel. Jerry cans have been around for a very long time, yet the main design haven't changed that much. There are some small things that have been changed, for instance the approaches and techniques for the coating, for the welding and others.
Made from strong treated steel, the first stage is the cutting of the can's shell. Once cut, the sides are sent for stamping, where grease is added before they are pressed into shape, forming the sides of the can. The excess steel is quickly cut away by guillotine, before the next machine is used to tidy the edges of the sides by crimping them. This cleaner edge is helpful for welding and helps keep the can airtight. A hole is cut into one side for the neck, then it's time for cleaning and degreasing.
When comparing the can that was invented in 1936 with the can that we have now around, There are other differences. Also in the sizes, we have 10-liter cans and 5-liter cans as well.
The nozzle of the can is made from 3 separate pieces, which are all cut from this 8-stage press machine. It cuts each part out individually from a sheet of steel, and once cut, they are individually checked by hand before being sent for spot welding. Spot welding is where 2 copper electrodes pass a current through the metal that is strong enough to weld it together in seconds. Here, the nozzle cap, breathing channel and special bayonet locks are welded and date stamped. The handles are also formed by machine press from pre-cut sheets that were made by a CNC machine.
Our company is producing jerry cans since 1959, that is for civilian use, and also military jerry cans since 2000. So during this period of time, company has produced almost 30 million jerry cans. And in this total sum, it's also almost 1 million for different NATO armies.
Once the side panels have been cleaned, it's time for the main process of production. The neck of the can is welded into place, along with the breathing channel that is welded into the inside of the can. This unique inclusion on the inside of the can enables glug and splash-free pouring by creating an air pocket. Both sides of the can finally meet and are pressed together by machine before being sent down a track where they are put through full body welding. Using a combination of arc and mag welding, the 2 sides are firmly bonded together. The unique 3-handle design is also attached to the roof of the can. Due to the often flammable contents of the can, this is a very important process, so many spot checks are carried out to make sure the seal is complete, including a water test to check for bubbles, making sure the can is 100% airtight. The cans are washed and sent for painting. First, a special petrol-resistant alkyd ammonia paint is sprayed internally to prevent rusting. Then the outside is given an anti-corrosive powder coating, which protects the can and gives it a smooth look finish. The cans move into a ginormous oven and are heated to temperatures of 200 degrees to solidify the powder coating.
Jerry can has become very popular for creative ideas. We have seen jerry cans used for the suitcases, vases, bar chairs, mini bars, and many others. There are different approaches to use the jerry can in the design, so it's a very iconic product. Even big fashion brand Chanel use it as a handbag.
All final checks are made at the packaging area. All seals, pins and locks are tested before being packed and shipped to civilians and military personnel alike all over the world.
Maybe jerry can seems very simple product, yet it requires 80 different operations to produce one single jerry can.
The jerry can, truly a wicked invention. So there you have it, a dash through the hidden history, super science and amazing manufacture of products that you use every day, but have never realised their amazing background. Radio, silly putty and the jerry can, all wicked inventions.